Welcome to The Explainer. We usually just picture spaceflight as finally reaching that perfectly peaceful, silent vacuum of space, right? But before any vehicle can even touch that void, it has to survive an absolute gauntlet. It's an immense, unseen physical battle right here at home. So today, we're diving straight into atmospheric engineering and exactly what it takes to survive Earth's atmosphere.
Okay, let's dive into this. If we map out our chronological flight profile, it really reveals a continuous journey of extremes. We're starting completely stationary down on the launch pad, then we have to punch our way through the thick atmosphere, survive the immense structural stress of max Q, and finally reach the insidious, near-vacuum environment of low Earth orbit. Here is our flight plan for today. We'll be looking at weather on the pad, battling aerodynamic drag, surviving max Q, beating aerodynamic heating, and wrapping up with the hazards of low orbit.
Part 1. Weather on the pad. Pre-launch hazards.
Before those engines even think about igniting, the atmosphere is already acting as a heavy gatekeeper. Just think about the number 101.325. That is the baseline atmospheric pressure in kilopascals right at sea level. We walk around in this pressure every single day, and honestly, we don't feel a thing. But to a towering space vehicle, this invisible air is incredibly heavy. It's dense, it's tangible, and it is literally pushing in on the rocket from all sides. And all that heavy air brings some serious complications. We're talking about launch scrubbing weather conditions here. Things like cloud cover, rain, humidity, low visibility, and most dangerously, lightning and wind shear. Lightning is an absolute deal breaker for sure, because a single strike can completely fry onboard electronics, scramble communications, and trigger catastrophic electrical discharges. Meanwhile, strong winds, especially crosswinds, can literally cause the massive vehicle to bend. That increases aerodynamic loading and messes with flight stability before it even leaves the ground. This is exactly why they use weather balloons and radar systems to constantly measure wind profiles before every single launch. If the weather isn't playing nice, the launch gets postponed. Period. Part 2. Battling aerodynamic drag. Overcoming air resistance. As the rocket climbs and atmospheric density drops, rocket nozzles actually start operating more efficiently. Now, what's really interesting here is what happens to temperatures on the way up. You'd probably guess it just gets uniformly colder the higher we go, right? Actually, no. In the troposphere, sure, the temperature decreases with altitude, but then you hit the stratosphere and it actually increases because the ozone there is absorbing ultraviolet radiation. Keep going into the mesosphere and it drops again, only to sharply increase once more in the thermosphere because of solar radiation absorption. It's a roller coaster. These completely unintuitive temperature fluctuations are exactly what dictate a launch vehicle's entire thermal design and material selection. But alongside those wild temperature swings, we have to deal with the brutal force of aerodynamic drag. It's kind of like trying to sprint through waist-deep water instead of running through thin air. The standard drag equation shows us that this opposing force relies heavily on atmospheric density, the vehicle's velocity, and its shape. And this is precisely why launch vehicles absolutely require highly streamlined configurations and perfectly smooth outer surfaces. We literally have to slice our way through that dense lower atmosphere to reduce this massive opposing force. Part 3. Surviving max Q. Peak dynamic pressure. So the rocket is accelerating incredibly fast at this point, but the air around it is still dangerously thick, which begs the question, what happens when maximum speed meets maximum air resistance? Well, something has to give. You've got this massive vehicle pushing harder and harder against a literal wall of air that is pushing right back. So, the crucial point is what we call max Q, or maximum dynamic pressure. This is the exact moment during ascent where the combined effect of atmospheric density and the vehicle's velocity produces the absolute highest aerodynamic loading and structural stress on the entire rocket. It's a make or break moment. To survive this peak structural load, engineers actually have to temporarily reduce engine thrust. They're literally stepping off the gas pedal and carefully control the guidance system so the rocket doesn't just tear itself apart. Max Q is an absolutely critical design condition for any launch vehicle. Part 4. Beating aerodynamic heating. High-speed friction. Let's move to and see how this builds. Once we push past max Q and enter hypersonic flight, things get incredibly hot. As the vehicle travels at extreme speeds through the upper atmosphere, the sheer friction and compression of the air generates severe heat. We're talking about a massive physical threat here to structural materials, delicate electronic equipment, and those payload fairings that are protecting the cargo. Because of this intense heating, we have to use heavy, highly specialized thermal protection systems and advanced heat-resistant materials just to keep the rocket from sustaining catastrophic damage on its way up. Part 5. Hazards of Low Orbit. Residual Atmosphere. We finally make it above 100 kilometers, but wow, what a stark difference between our environments. And this brilliantly illustrates the shift. Down in the lower atmosphere, you're battling violent, highly visible forces, high drag, severe heating, heavy pressure. But up in low Earth orbit, or LEO, the threats become silent and insidious. Even though it's a near vacuum, there are residual atmospheric gases floating around that introduce two major sneaky hazards: atomic oxygen erosion and orbital decay. Let's look a little closer at these silent threats. Up in low Earth orbit, you have this highly reactive atomic oxygen present. It's invisible, but it literally erodes spacecraft surfaces over time. It damages polymers, degrades paints and coatings, and can dramatically reduce the efficiency of solar panels. Engineers have to use specialized atomic oxygen-resistant materials and protective surface coatings just to keep the satellites functioning. And on top of that, the tiny amount of residual atmospheric drag up there slowly, almost unnoticeably, saps the spacecraft's orbital velocity. Because of this drag, the orbit altitude slowly decreases, and satellites will gradually spiral back toward Earth. It's a process called orbital decay, and it means we have to do periodic orbit corrections just to keep things aloft.
To wrap all of this up, let's look at this quote based on our source data. A proper understanding of atmospheric conditions enables engineers to reduce structural mass while maintaining safety and increase satellite operational life. Mastering this environment, from the crosswinds on the pad down on Earth to the atomic oxygen way up in orbit, is the mandatory first step. Every aerodynamic shape, every thermal tile, every weather balloon sent up, it's all about outsmarting the atmosphere to predict loads, improve launch success rates, and ensure the mission actually succeeds.
Which leaves us with this final thought. If we have to engineer such massive, complex protections, the streamlined shapes, the intricate thermal systems, fighting all that heavy atmospheric resistance just to safely leave our own Earth, how on earth must we design ships to survive the incredibly dense or toxic atmospheres of other worlds? It's a pretty fascinating engineering challenge, right? As we've seen today, mastering our own sky is really just the beginning.